Today we will talk about double integrals in polar coordinates. So we talk about the iteration method on Monday, and also we define the x simple and y simple domains. Iteration of some double integrals in Cartesian coordinates may be extremely complicated. So those ones that we deal with can be complicated. So for such domains, we can use another methods. For example, if we consider the solid below the paraboloid that you can see here, x squared plus y squared, above D, the unit disk, which is x squared plus y squared smaller equal to 1, then the integral that gives the solid of the volume of that solid is defined by that double integral, as we define on the first chapter of double integration, x squared plus y squared over d, and we know d is the unit disk. So if we try to write it in Cartesian coordinates, it will define by such a double integration, but it is not easy to compute, so it requires a considerable effort. Can use the computation of the integral by introducing açık. So we can compute the integration by introducing a new coordinate system, which is called polar coordinates. So how we can do it? Sesim bana geliyordu arkadaşlar. Bir baksanız. Bir mikrofon açık kaldı. So how can we define that polar coordinates? So any point in Cartesian coordinate system, any point P, can be defined as xy, right? So can be defined by those coordinates, and also it can be defined by, as you can see here, R and alpha. So R is here the distance between point P and the origin here, and theta, as you can see here, is the angle made by the positive x-axis of the line passing through the origin. So this on that side. So of course here theta is not specified for the origin if you take the point as origin. So those two will be equal. So if you can define any point in Cartesian coordinates as xy, in polar coordinates you can define any point P as r and theta, where r is the distance between P and origin, and theta is the angle made by the positive x-axis of the line passing through the origin and P. So by this definition of P, okay, so this is in polar coordinates as we said. So these coordinates are actually related by these equations. So as you can see also, let's see again in the figure, you can just write x, the x coordinate of the P, the point P on Cartesian coordinates, as r times cosine theta, and also the y coordinates of P at Cartesian coordinates as r times sine theta, this side. So you can directly write those, and also we know that from also the sketch above, from the Pythagorean theorem, r square equals x square plus y square. Of course, where the theta is an angle between 0 and 2 pi, and r is greater or equal to 0. So if we try to give some examples, for example, if he has Cartesian, he has, let's say, coordinates in Cartesian coordinates as -1 square root of 3, then that means from those equations we have, that means r is 2 and theta is 2 pi over 3. So this is how you define P in polar coordinate system. And if you talk about all the points in D, which is a unit circle, x square plus y square equals 1, and also half unit circle where y coordinates are greater or equal to 0, then that region can be specified on polar coordinates as r equals 1 and theta is in between 0 and pi. And the last example I guess here, okay, is the region in Cartesian coordinates system is specified by that sketch above. So the shaded area here is the sketch of D, which is, as you can see, 1 is smaller or equal to x squared plus y squared smaller or equal to 4. So this is the shaded area in the figure. And you can also define all the points on that shaded area, let's say, in polar coordinate system as r is in between 1 and 2. So r is from 1 and 2, and theta is in between 0 and 2 pi. Okay, 0 to 2 pi. So if you just sketch that shaded area in r theta plane, then it will represent now a rectangular region. So why we try to define those areas or points in polar coordinates, maybe especially areas here, because it is much easier to calculate double integration in x and y simple domains. So as you can see in the third example here, when we write the shaded area in r theta plane in polar coordinates, that means So we found a x and y simple domain, right? So it is now easy to calculate through that region the double integration. So let's see how we can write double integrals in polar coordinates, and we will compare the form of area elements in Cartesian and polar coordinates. So, okay, we define the area, but also we need to define dx times dy in r theta plane in polar coordinates. So let's try to define it also. So if you just look in the first sketch here, the shaded area represents delta A, which is delta x times delta y, and also it represents dA, which represents dx times dy. And if you just look the second figure, the shaded area here so if we call it delta A, it is approximately equal to r times delta A, that this is that arc here, and times delta r. And from this definition we can write dA as r times dr times d theta in polar coordinates. So if you just look again how we define dA in Cartesian coordinate plane and also in polar coordinates, there is of course there will be difference. So dx times dy, it is in dA in polar coordinate in Cartesian coordinate system, and as you can see in polar coordinate system we define dA as r times dr times d theta. So that means the double integration over d in Cartesian coordinate system is equal to, from the definition that we had above and also from the definition of dA we have seen in the figure, it will be equal to f r cos theta r sin theta times r times dr times d theta, which is dA. So that comes from, if you write x in polar coordinates, we know that it is equal to r times cosine theta, and y equals r times sine theta in polar coordinates, and dA is equal to r times dr times d theta. So of course we don't need to sketch all the regions that we try to integrate our function on polar plane, RQ plane. The polar coordinates can be read from the sketch of the region on xy plane. We can directly write them through the sketch in Cartesian coordinate plane, so through xy plane. But of course we shouldn't forget the factor here on dA. Okay, we have the factor r, So let's try to see over an example. Find the volume of the solid below the paraboloid and above the unit disk. So we need to evaluate in, if we just define it in Cartesian system. So it is the double integration of fxy, which is x squared plus y squared, the paraboloid, over d, which is the unit disk. But we said that it requires considerable effort. So now we will try to evaluate that integration in polar coordinates. So since the integration domain, or D, is the unit disk, which is shaded here, that one. So we can evaluate that region in Cartesian, as well in polar coordinate system, like that. R is between 0 and 1, so that means from 0 and 1, and the theta is between 0 and 2 pi. So this is the region which is the unit disk in Cartesian system in polar coordinates. Okay, so that will be the integration domain, let's say. And of course we will have to transform x and y in a polar coordinate system, and if of course dA. Okay, so if we try to write the integration that we want to compute in polar coordinates, then r x squared plus y squared is equal to r squared, and dA equals r times dr times d theta. So if you just multiply r squared by r, you can write as r over 3 here. And sorry, from the integration order, if you start by dr, so as a limit of integration, you have to write the limits, the borders of, let's say, r, which is, let me set here, in between 0 and 1. And after that, you have to write the borders of theta, which is in between 0 and 2 pi. So that means the lower integration, the limit of integration will be 0, and the upper limit will be 2 pi. Then after that, you will just compute the inner integral here, so which will be r over 4 from 1 to 0. So after you compute this, then you will compute, of course, the other integral, definite integral here, and it gives you pi over 2 unit cubes, since it is a solid. If we try to, the volume of the solid that we try to compute.
Ses cızırtılı ve robotik geliyor.
Şu anda nasıl sesim arkadaşlar? İnşallah düzeldi.
Daha iyi geldi.
Yani şimdi senin sesini de alabiliyorum Ece ben. Biraz önce yankılı yapılanıyordum. Beni uyarın yine bir şey olursa. Sanırım artık bilgisayarla alakalı da bilgisayarlar da error vermeye başladı. Kayıt devam ediyor galiba aldığımız. Evet, kaydediyor. Ben kaldığım yerden devam edeyim. Dediğim gibi yine seste problem olursa beni uyarın. Şu dosyayı açmam lazım. Geldi mi slide şu anda? PDF.
Ben göremiyorum slaytı.
14.4.
Şimdi geldi hocam.
Tamam, biraz zaman aldı demek. Tamamdır. Birinci örneği bitirdik aslında. Tamam, 1 bölü 2 dedik. İkinci örnekten devam edelim. Yine polar koordinatta tanımlamayla yapacağız örneği de. Find the volume of the solid lying inside both the cylinder here in the sketch, which is shaded by red, x square plus y square equals 4, and the sphere x square plus y square plus z square equals 16 in the first octant. So this is important here, in the first octant. So this will be the volume of the solid, which represents the below, it will be, or let's say lying inside both the sphere here, but it should be in the first octant, so you can think is like that, and the cylinder x square plus y square equals 4. So this is the, I cannot shade again, this is a region which is shaded by red here. Okay, so to represent it is in the first octant. Also, as you can see, we write x is greater or equal to 0, y is greater or equal to 0. So, okay, I will clear those. So that will be the, let's say, a part of, let's say, a part of, or a slice of cylinder. Okay, like that. I will try to show. So this will be çizemiyorum. Neyse kalsın o zaman. This is a slice of the solid which is inside both the sphere here and the cylinder, but only in the first octant. So that is why I called it as a slice. So we sketch it here, but you don't need to do that sketch, but you should sketch the region, okay, the region that you try to calculate your double integration. So the solid lies below. If you just write the definition of the sphere, so from here z, which is fxy, which is our function here, this one is square root of 16 minus x square minus y square, and above the shaded region here, okay, the shaded region D. So in polar coordinates we have to define that shaded region, which is defined as you can see in in xy plane in polar coordinates. So if you just sketch that, or you can see it from here actually, this is, so here is 2, so R has to be in between 0 and 2, and since it is only in first octant, the theta has to be in between 0 and 2 pi. So it is from 0 to 2 pi. Burada çok küçük olduğu için alan çizemedim ama şu kırmızı taralı bölgenin D olduğunu biliyoruz. Çünkü sadece birinci oktantta hesaplamamızı söylemiş soruda. Bu ikisi arasında kalan bölgenin hacmini. O halde şurada kırmızı taralı bölge zaten x-y koordinat üzerinde burada yazdık. Polar koordinatta da nasıl tanımlanacak? 2'de kesiyor. Değil mi? Burası 2 aslında. Şöyle yazmaya çalışayım. So here is 2, right? Here is 2, and also of course here is 2. So if you suppose this is the region D, so it can be represented on polar coordinates, okay, as R in between 0 and pi, and theta, since it is a shaded area in first octant, it has to be from 0 to pi over 2. Okay, so let's close it. So if we try to write again the double integration that we want to find, it will be square root of 16 minus r square, because here you can write the fxy as square root of 16 minus x square plus y square, so you can directly write fxy in fr theta, and we already seen that dA is equal to r times dr times d theta in polar coordinates. So after you write that, you need to start by integration with respect to r, okay, and the limit of integration has to be from 0 to 2 at here, and after that you have to write the limit of integration with respect to theta, so which is from 0 to pi over 2 here. So we can write now the limit of integration for theta. Then you need to compute the integration. First you will compute the inner integration, this one, and here you need to use substitution method, where you take u as 16 minus r square. Then after you compute this integration, you can compute the outer integral. Okay, we change the variable xy into r theta in polar coordinates, but also you may change as any variable that you can express as u and v. So the transformation of double integral in Cartesian coordinates to polar coordinates is a special case of change of variables in double integrals. So it is in r theta. If we suppose that x and y are substituted by some expressions u and v, so we will let u and v. So we try to write x as a function of u and v, and y as a function of u and v, as we did in polar system in r and theta, like that. So we may see the change of variables as a transformation from uv plane to xy plane. Okay. So if we consider the domain here, which is represented by S, and R is in between 1 and 2, theta is in between pi over 4 and 3 pi over 4 on the r theta plane. So it is of course in r theta plane. This is the shade sketch here. The S is here, the shaded area. So S is indeed a rectangle on r theta plane. So it is r and theta simple. So it is that shaded rectangular area, and in that by that transformation, as we did for polar coordinates, you can see that it represents that shaded area in xy plane, so which is defined as 1 smaller equal to x squared plus y squared smaller equal to 4, and y is greater or equal to absolute value of x. So the transformation of polar coordinates transform S from the r theta coordinates to the domain D lying between the circles and lines y equals x and y equals minus x. So that is why we define it as y equals right greater or equal to absolute value of x here. So in particular, this transformation from S onto that D is 1-to-1, and any point in D is the image of a point in S. So any point in D here, so any point in D here is an image from a point on S. So that is why we can have a one-to-one relation. So in general, we can have such a transformation from a domain S on UV plane onto D on XY plane. Then we may apply the change of variables as our assumption in double integral. And the other thing that we need to modify is dA, which is dx times dA in Cartesian coordinates. But we need to define them dA in terms of du and dv. So it is summarize the change of variables rule, but we will summarize it in the next theorem, but we will not show the proof. So it will show us how we will define the dA in terms of u and v. So if it is your transformation, or if we let x as a function of uv and y as a function of uv, be a one-to-one transformation from also S onto UV plane, on the UV plane, onto D on XY plane. And if we suppose that XUV and YUV have continuous first partial derivatives on S, then dA, which is dx times dy in Cartesian coordinates, is equal to the Jacobian determinant that we have seen before. So it is the Jacobian of lambda xy over, let's say partial xy over partial dv times du times dv. So that is the determinant, Jacobian determinant of transformation that we have. So if we now try to express the double integration over d onto s, so by this transformation it will be equal to this integration. So this will be f xu y xuv yuv. So because you have this transformation now, this one, and then instead of dA or instead of dx times dy, you have to write the Jacobian determinant of transformation times du times dv. And if we remind the calculation of Jacobian determinant, okay, this is the absolute value also. This is the absolute value of Jacobian determinant. So the Jacobian determinant is, if we remind it again, it is the determinant of matrix 2 times 2 matrix with first row partial of x with respect to u, so this one, and partial of x with respect to v, and second row partial of y with respect to u, partial of y with respect to v. So this is the Jacobian determinant that we have seen for the calculation of partials, and also solutions of systems. The Jacobian of transformation. Okay, let's see if we already computed the A in polar coordinates in a right way. So if we check also by using Jacobian determinant, so that means we have to compute the Jacobian determinant of this transformation. So this will be equal to the first partial of x with respect to r, which will be cosine theta, the partial of x with respect to theta, which will be sine theta, and the partial of y with respect to r, which is minus r times sine theta, and then the partial of y with respect to theta, which is r times cosine theta. So if you compute the determinant, it is r times cosine square theta minus r times sine square theta, which will be equal to r times 1, so which is r. So that means the dA that we showed by the sketch also can be found by Jacobian determinant in terms of r and theta, so which is in polar coordinates, which is r times dr times d theta, because you will take the absolute value of r times dr times d theta from the definition we have here. Okay, from that definition. So, okay, the term here we have is the absolute value of Jacobian that we said, and the transformation x equals x uv, y equals y uv transforms the region S that you can see here on the uv plane to the region D on xy plane. So by this transformation, but in terms of change of variables, we transform an integral with respect to dx dy to the integral with respect to du dv. So this is what we do. So we will now try to find that integration, try to define the integration by using that transformation in that way. And the theorem that we had seen still solves for the transformation on the boundary of S, even it is not one-to-one there, because, okay, let's say again here on the sketch, for example, here you have a specified domain S, which is that shaded region. R is in between 0, 1, and theta is in between 0 to pi on r theta plane, of course, and we will map this mapped onto D, which is the unit disk here on xy plane under polar transformation, polar coordinates transformation, and the boundary of S that region S is the rectangle with sides, of course, r equals 0, which will be theta plane here, r equals 0, r equals 1, this one, r equals 0, r equals 1, so those are the boundaries of S. Theta equals 0, theta equals 0, the other boundary, and theta equals 2 pi. So those are the boundaries of S. Sesim yine mi bozuldu? Tamam, çıkabilirsiniz. Ders olanlar çıkabilir. Ben biraz yani bu section'ı bitirene kadar biraz uzatacağım dersi. Çok fazla sayfamız kalmadı zaten. Çoğu da graf da var. O yüzden dersi olanlar çıkabilir. Sonra kayda bakabilirler. Son 4 sayfa için. So now we will try to see even the boundaries are not one to one. It will not affect the calculation. It will not affect the theorem. Okay, so the boundaries of S are those sides that we sketch, and the side r equals 0 is mapped to the origin. So r equals 0, this one, is mapped, as you can see, to the origin on xy plane. And also any point, any 2 points are 0 and are 2 pi. So r can be any value in between 0 and 1. So those 2 points, this is r0, that one. This one is r0. This one, and this one is r2 pi. Let's suppose that. And that can map into, as you can see, into the same point on xy plane. So we can map to the same point on xy plane, but it will not cause any problem by the calculation of double integration. Actually, we talked about that on previous course. Can anyone has idea about what is the value of the integral on the boundary? Bu sınırlarda arkadaşlar integralin değeriyle ilgili ne söyleyebiliriz? Şuradan yola çıkarak birebir olmaması bu mapping'de bizim için bir problem teşkil etmiyormuş. O zaman buradan yola çıkarak ne diyebiliriz bu soru için? Var mı fikri olan? Geçen dersi aslında söyledik bunu. Hatırlatmak için eklemişiz buraya. Var mı fikri olan burada? Sıfır oluyor arkadaşlar. Since it is 0. Okay. That is why it is not effect. It does not affect the double integration. And as I said in the beginning, the main aim to use those transformations for double integrals is to simplify the domain. So to get a simple domain, x simple, y simple. So if we have the right transformation, we can find in any UV plane a U simple domain or V simple or both generally we try to get U and V simple domain. So in general, it will be helpful to look for transformation, as I said, which transforms the domain to a simple domain. So such as rectangles, discs, or extra, that kind of simple domains. So for example, if we try to find the area of the elliptic disk E for A be positive, then if you try to write it in Cartesian coordinates, it define, we said that, it define the double integration of 1 over E, so that will give you the area of elliptic disk E. But it needs suffer to compute that integration. So after using the transformation where we let x as equal to AU, A times U, and Y equals B times V, and we transform the unit disk U square plus V square smaller or equal to 1 onto UV plane onto the elliptic disk E. So by using that transformation, this one, we can transform S onto E. So that means we can compute the area of that elliptic ellipse or E or by using the transformation over S. But first we need to define dA in terms of U and V. We need to find the Jacobian determinant, so which will be the determinant of the 2 times 2 matrix by the transformation x equals A times U, Y equals B times V. So from that transformation, we have the Jacobian determinant as A times B. So that means the area of E that can be calculated by this in Cartesian coordinates is equal to the determinant of, you can write 1 here or it doesn't matter, the absolute value of the Jacobian determinant, which is the absolute value of A times B times du times dv over, so it is like double integration over S, so which is equal to absolute value of A times B times, this is a constant, A and B are positive constants, sorry, so you can let that constant be for the integration, right here, and then you need to compute actually the double integral of 1 over S, so which is the area of S, so the area of S. So what is the area of S after that transformation? That is, so the area of S, since area is a unit disk, pi times 1 square, so which will be pi. So that is why the area of that ellipse is equal to pi times A times B. So I guess this is the last example. Yes, okay. Here we have one more transformation on UV, but here let's see how we will choose the transformation. So evaluate the double integral of fxy, which is 9x square minus y square over the parallelogram determined by lines y equals 3x, y equals x plus 2, y equals 3x minus 8, and y equals x plus 4. So this is the area, let's say D. This is the parallelogram. So this is the domain on the sketch. So it is possible, of course, from on xy plane, it is possible to calculate that integration, but we have to do it into 3 parts. So the first part has to be here, this one. So the second one is here, and the third one is the other side of the parallelogram. So we have to separate the parallelogram region here into 3 parts. So it will take time to that kind of computation. So we will try to make it easier to compute by transforming the domain into a rectangle. So we will try to transform that domain into a rectangular region. So if we express our region above as 0, 3x minus y in between 0 and 8, and y minus x in between 2 and 4. Those are the boundary lines. So the substitution as u equals 3x minus y is 1, and v equals y minus x, so which actually, in other words, can be written as x equals u plus v over 2 and y equals u plus 3v over 2, simplifies the region, parallelogram region, to a rectangle in UV plane. So by that transformation, that D, so by this transformation, let's say, that the rectangle, it will be transformed onto a rectangle where u is in between 0 and 8, and v is in between 2 and 4 on UV plane. So now the last thing that we should do to define A in terms of u and v by this transformation. So if we compute the Jacobian determinant, we find 1 over 2, and after that, of course, we need to write our transformation. So fxy becomes f u plus v over 2, u plus 3v over 2, and then here we need to write, instead of dA, the absolute value of Jacobian determinant times du times dv, so which will be 1 over 2 times du times dv. And of course, since f is 9x square minus y square, so this was the function. So after this transformation, this one, it will be 2u square. Of course, you will compute f again in terms of u and v by the transformation we had, then it will be 2u squared plus 3u times v. And then, okay, you can just let 1 over 2, or the absolute value of 1 over 2, be for the integration here. And you need to write the limit of integration, first with respect to u, then with respect to v, by the transformation we have here. The limit of integration with respect to u is 0 to 8, and for v it is 2 to 4. So from 0 to 8 and from 2 to 4, and first computing the first or inner integral, then after that computing the outer integral with respect to v, you can find the double integration of fxy over the parallelogram, but which we transform into a rectangular region on UV plane. Tamam arkadaşlar. Burada bırakalım. Var mı UV transformda burada sorun? Ne kadar?